Hey everyone, in this video we're going to start topic 7 and we're going to be discussing, particularly in this video, electronegativity, but then in later videos we're going to move on to dipole moments and polarity, and then eventually we're going to talk about solubility of molecules as well. So last chapter we talked about greenhouse gases. We had discussed that some molecules in the atmosphere can absorb IR radiation from the sun, and that's what causes them to be a greenhouse gas, because then they heat up. But some molecules in the air don't. So in particular, these two don't absorb IR radiation. These do. So what causes some molecules to absorb IR radiation and other ones to not? We had discussed that it has to do with the frequency at which these molecules vibrate. That is true. Another thing that determines the frequency that they vibrate at is the molecule shape. So is it a line? Is it here kind of in this bent shape, or does it have four constituents off the side of it? The identities of the atoms inside of the molecules. One of the things that determines whether or not it actually absorbs that IR radiation is when the dipole moment changes. So you might be wondering, what's a dipole moment? What does that mean? We're going to cover all of that in just a minute. So what this means is that these molecules here that don't absorb IR radiation don't have a dipole. But these molecules that do absorb radiation, they do have a dipole, which is an important distinction between these molecules and how we can determine whether or not they're greenhouse gases. So let's take a look at some of the vibrational modes of carbon dioxide, which is a greenhouse gas. When carbon dioxide is hit with IR radiation from the sun, it vibrates, we know that, but it vibrates in different ways. And it vibrates in these four different methods that we see here. So the oxygens, these are going to be the oxygens on the side. This intersection here is going to be the carbon in the center. So the whole molecule itself can stretch out like this, with the oxygens moving on the side. It can bend, as shown in the third and fourth diagrams, where you can kind of see it go out like this, or like this. It can bend this way. Or you can have what's called an asymmetric stretch, where the oxygens stay put, but the carbon moves. So the carbon would go from one side to the other, kind of like this. And so it can vibrate in different ways. And what's interesting about these vibrations is some of these vibrational modes have a dipole, others don't. So this one here does not. No dipole here. These do. These have dipoles. And so what that means is whenever it's hit with these vibrational modes, it can go from dipole to no dipole, dipole to no dipole. And that's what causes it to absorb IR radiation and have the specific vibration that it needs in order to do that. So what is a dipole moment? Since I've been talking about this, what is a dipole inside of a molecule? What does that mean? So this is an uneven distribution of electrons inside of molecular compounds, inside of molecular molecules or molecular compounds. So you might have heard it as covalent compounds. So molecular / covalent compounds. This is where you have things like water molecules over here, where we have a hydrogen, oxygen, hydrogen, and these electrons are shared between the atoms. Sharing. So they share electrons, sharing electrons unevenly. So when they're shared evenly, there's no dipole. When they're shared unevenly, there is a dipole. So in a covalently bonded molecule. All right, so hopefully you caught that there. Make sure you write that down. Right, so certain parts of this molecule, this H2O molecule, are more positive or negative than others because of this uneven sharing. So what's happening here is this is our, it says electric density, it's our electron density, And remember that electrons move really, really quickly, so it's kind of hard for us to pinpoint their location. We can say, oh, well, they're kind of in this area. We can't exactly say that they're right there. We can say there's a high probability they're over in this area somewhere. And so this is an electron density map that shows the probability of where these electrons are going to be. And as the waves get darker, you can see that that's where the electrons are more likely to be. So we have more electrons around our oxygen, and it gets lighter and lighter as we go further and further away from the oxygen, say out towards the hydrogens. So there are electrons out at the hydrogen, there's just a lot less. And so what this causes is an uneven distribution of charge inside of the molecule, because electrons are negatively charged, right? So if we have a bunch of electrons around one particular atom, that one particular atom is going to be more negative, which is represented by this partial negative charge. If there's less electrons, then they're going to be relatively positive in relationship to our negative side. Okay, so we dictate this as partial charges. So this symbol here means partial charge. Partial. So we could say a partial positive in this case, or a partial negative in this case. Partial negative charge. So it's not a full negative or a full positive, it's partial. It's just a little bit. And so just like a magnet, when you have a positive and a negative end of a magnet, and say this is our water molecule, and we have another water molecule that also has a positive and a negative end, these things are going to interact with each other in solution. So they're going to actually line up. They actually do this. So the positive end aligns with the negative end on another molecule. So they might be rotating in solution, and then when they get close together, they're going to line up, and they're going to kind of stay like this. They aren't going to orient this way. The positive's not going to go to the positive end. It's going to be oriented the other way. So each molecule inside of our, say, like a water droplet is actually kind of lined up pretty well, and they interact with each other. When one moves, the other one kind of moves. So if they're close together, they will kind of be like sticky. So it's not necessarily a full covalent bond, but it's kind of like a transient bond in between the two water molecules that exists. This is what we call intermolecular force. We're going to talk about it in later chapters. But that's what these partial positive and negative charges do. They cause the molecules to interact with each other. So just to be clear, I do want to make sure that you understand the difference between a full positive charge and a partial positive charge, or partial negative and full negative charge. So unlike ionic compounds, in ionic compounds, like NaCl, these compounds split into full charges. An electron fully translates from one to the other. Electrons are not shared. No sharing of electrons. What's actually happening is an electron is fully transferred from one atom to the other. So we end up with Na plus and Cl minus. That is a full charge separation. That is a full charge. So if it's a full positive, oh my goodness. If it's a full positive, you'll see it written as a positive. If it's full negative, you'll see it written as a negative. If it's a partial positive, you'll see it written like this. If it's a partial negative, you'll see it written like this, okay? So here's kind of another example of electron density and attractions around atoms. So we can see here that as our hydrogens are bonding to our oxygen and our water molecule, that once they're bonded, the electrons still reside primarily around the oxygen. So the oxygen hogs all of these electrons, and it just in general has more electrons than these hydrogens out here, which aren't going to have very many. So let's examine what might be causing this. So I'm going to ask you to propose a theory. You can model this yourself, or you can use atom.phys on your iPad. This is a free app. I like it just because it helps you see the structure of stuff really easily and clearly. So I'm going to ask you to examine hydrogen and oxygen on your periodic table and suggest a theory as to why oxygen atoms pull more strongly on their valence electrons, on valence. Let me clarify this. This is valence electrons. So that's their outer electrons. So look at the number of protons, look at the number of neutrons, look at the number of electrons, look at the number of electron shells in order to figure out why you might see that your valence electrons, the outer ones, are being pulled more strongly with oxygen versus hydrogen. Okay, so let's also do that for fluorine and chlorine, because there's another trend here we're going to talk about in a little bit, and I want you to think about it first. So let's take a look at fluorine and chlorine here. So fluorine pulls more strongly, I don't even know if that's a word, on valence electrons. So your job here is to propose a theory as to why fluorine atoms pull more than chlorine atoms based on their structure. So you can model these in atom.phys to see what they look like, or you can just rate them out, because you should be able to determine this on your own. All right, protons, neutrons, electrons, and remember your electron shells. You'll want to examine that as well. Okay, so see if you can do your best. It's okay if it's wrong, but think about this concept and think about why fluorine might pull more strongly on its valence electrons. So let's discuss the answers to these. So in the first one, you were looking at hydrogen and oxygen. If you modeled these in atom.phys, you might see some really big differences. So hydrogen has a single proton in the center, and it has one electron around the outside of it. Okay. All right, so that's your hydrogen. Let's look at our oxygen. So oxygen has 8 protons right here in the center. 1, 2, 3, 4, 5, 6, 7, 8 protons in the center. We are going to look at neutrons because neutrons have no charge, and they aren't going to be affecting pull because we're thinking of magnets, positive and negative charges. So we aren't looking at something that doesn't have a positive or negative charge. Okay, so oxygen here has 2 electrons in its first electron shield here. And then it's got 1, 2, 3, 4, 5, 6 in its next electron shell here. 1, 2, 3, 4, 5, 6. Okay, so oxygen pulls a lot more on these 6 electrons here, these valence electrons here, than hydrogen does on its single valence electron here. One reason for this is you can see that the nucleus inside of oxygen just has more positive charge. So because there's more positives, it's going to pull more strongly on its negative charges. That's a given. And so that's why we see that trend there. Let's take a look at fluorine and chlorine. Right? Fluorine and chlorine right here. This is an electron density map here. Electron density. You can see that the electrons around the fluorine are red, so the density is more compact around the fluorine, it's tighter, whereas around the chlorine it's a lot looser and it's yellow, so it's not as dense. So this one here has a higher electronegativity, it pulls more strongly. So why does fluorine pull electrons towards itself more strongly than chlorine? Fluorine has 9 positive charges in its center, and it has 2 electron shells around the outside. So it's got 1, 2 electrons in its first one. 1, 2, and then it's got 1, 2, 3, 4, 5, 6, 7 around the next one. Okay, that's our fluorine. Let's take a look at chlorine. Chlorine has 17 protons in the center. Okay, 17 protons in the center, so it's got a lot of positive charge, almost double the positive charge in the center of the fluorine. It's going to have our 2 electrons on the center as well. I'm getting that from here on the periodic table, from the hydrogen and the helium. Those are the first 2 electrons. And then we go to the next one. We have a full shell here of electrons. And then we progress down here, and there's 7 electrons in the next shell. Okay, sorry, I had to erase things and start over. Okay, so we have our 17 protons in the center of the chlorine atom. We've got our 2 electron shells. Now we're on our 3rd shell right here. There's 7 electrons in the next one. 1, 2, 3, 4, 5, 6, 7. Okay, so that's our chlorine. So there's some big differences here between chlorine and fluorine. So fluorine is much smaller. It has less protons. Chlorine is much bigger, it has more protons, it also has more electrons, but for some reason fluorine pulls a lot more strongly on its valence. So these electrons right here are pulled much more tightly than these electrons right here on your chlorine atoms. And so the reason for this is not because of protons. We have more protons in the chlorine than our fluorine. So if we base our assumption on the previous thing, then we should see that chlorine's pulling harder, but it's not. So what that means here is that distance is a factor. So this distance between the positive and the negative charges of the electrons is very important. So here, this is our distance. It's bigger in the chlorine. It's much smaller in the fluorine because of these electron shells. And so what's happening is because the fluorine has a positive and a negative charge and they can get really close to each other, it actually pulls a lot stronger. So again, think about the magnet example. Here's the positive, here's the negative. If you get your magnets really close, it's going to be really hard to pull them apart. But as soon as you put your magnets all the way out here, you're going to be able to pull those apart really easily. And that's the same thing with these electron shells. As you have more and more electron shells, your positive and negative charges get further and further away, and it's much easier to separate them. And so that's why they don't pull as strongly. So this concept is what we call electronegativity. This is an important definition. Electronegativity is how strongly atoms attract bonding electrons to themselves. So how strongly an atom will pull an electron to itself inside of a molecule. So inside of H2O, how strongly an oxygen, say, might pull an electron that's in these bonds towards itself. So this is determined by atom structure. We had discussed a couple of things that cause this. One of those is a larger nucleus. So having more protons inside of your nucleus is important. Now this is only important if you don't have more electron shells. So if you have more electron shells, that's more effective on decreasing or increasing electronegativity than increasing the amount of protons in the center. We saw that previously. So you might hear this called shielding. So electron shields, electron shells, they're the same thing, so don't get that confused. The other thing to know is that sometimes atoms don't pull on electrons. And this is determined by whether or not they have a full octet. So things say like neon or xenon or argon, these are noble gases. Noble gases have a full valence electron shell. They have 8 electrons, they have no holes, they do not need any more electrons, they are stable, and so these are not electronegative, not electronegative. They don't have any pull because they don't need more electrons. So that is something to just keep in mind as you're looking at things. Remember that our metals like sodium likes to get rid of these electrons entirely. It doesn't want to pull any towards itself. So these also have a low electronegativity. Whereas things like fluorine and chlorine over in our halogens category really want another electron. So they pull pretty hard in general on those electrons that are outside of themselves. Here's an example of all of your electron shells or shields. So you can kind of see how these build up as you go down the periodic table. So the first period here, we have 1 electron shell. You can see there's 2 electrons in it. As we go to the next period, there's another electron shell. We eventually work up to 8 electrons in it. The third one, there's a 3rd electron shell with 8, 4th, 5th, and so on. So this is how our electron shells build as we go down the periodic table. Let's discuss the Pauling scale. So this is an easy way to tell the electronegativity of an atom. So you might be asking, like, why didn't I show you this earlier and you could just learn the numbers? It's important to understand the concepts because sometimes you won't always have a Pauling scale. It's also important for speed on exams, so it's a lot easier for you to be able to eyeball something and be like, oh, I know the answer to that, as opposed to having to reference this chart all the time. So the Pauling scale, again, tells us the electronegativity of each of the atoms on it. So you can see that they're assigned a number. These are not mass values, these are electronegativity values. And in general, on our periodic table, fluorine is the most electronegative atom. I'm going to just write most En so I can stop writing this, okay? Most electronegative. And in general, all of the other atoms kind of build to fluorine. So we can see that our electronegativity increases as we go to the right on our periodic table. This happens because the increase in protons, remember we had discussed like hydrogen versus oxygen? This is the increase in protons taking effect here. Then over here, electronegativity increases this way. This has to do with our electron shells or shields. So electron shells or shields is decreasing. So therefore our positive charges can get a lot closer to our negative charges as opposed to larger atoms where they're like way out here, okay? And these electron shells are really effective at increasing the electronegativity or decreasing the electronegativity, more so than an increase in protons. And we can see that reflected in the numbers here. So if you look by going from one atom to another this way, we see a small increase in our electronegativity, whereas say we go from here to here, there's a bigger increase. From here to here, there's a bigger increase. So we can see that reflected in our Pauling scale. Another thing to notice on this chart, these guys over here, they don't have electronegativity values because they are very stable. They don't pull electrons towards themselves. These are noble gases. Okay, so give this a shot yourself. See if you can do this without the Pauling scale. You should literally be able to look at the periodic table snippet that I have here for you and answer these questions. So label the atoms in each question of order of increasing electronegativity, so from least to most, and then answer why you chose this order. Is it because there's an increasing amount of protons? Is it because of the shielding? Or is it because of an octet in the atom in particular? So give your best shot to these three questions. Let's take a look at how to answer these. So we have sulfur, phosphorus, and chlorine for the first one. Sulfur is here, phosphorus is here, and chlorine. Okay, so they're all in the same period or the row of the periodic table. So electron shells are not an issue here. They all have the same amount of electron shells. They have 3 electron shells because they're in row 3. So what's happening here, the difference is that they're gaining protons. So the most electronegative is going to be your chlorine, and the least is going to be your phosphorus and the sulfur in between because of protons. That's why. Now let's look at our oxygen. Oxygen, sulfur, and selenium. These are in the same group, i.e. column. So they have the same amount of valence electrons, not necessarily electron shells. They have the same amount of valence electrons. They do have different numbers of protons as well. Those are some of the differences here. What's particularly striking is they're in different rows, meaning they have different electron shells. So we're going to say this is due to electron shells. And we're seeing that our oxygen has the least amount of shells, so it's going to be the highest in electronegativity, followed by the sulfur, which is down next, and then the selenium, which is down next. So the more shells you have, the more shielding, the less effective that those positive charges in the center of the atom are at attracting negative charges way out here. So as you get closer and closer, it's easier to pull. All right, let's take a look at carbon, oxygen, fluorine, and neon. So we have carbon here, oxygen, fluorine, and neon. These are all in the same row, so they have the same amount of shields or shells, which is really nice. We need to look at our most electronegative. We know that's fluorine. Fluorine is the most electronegative atom on the periodic table. It's definitely that one. The next thing that we want to look at is increasing number of protons, right? Because we're going across a row. So you might think that neon is the most electronegative because it definitely has the most protons here, right? But remember that neon has an octet. So it actually has 0 electronegativity, which means it's the lowest on our scale here, just because of that one exception. So this is kind of an exception to the rule. And then we have carbon and oxygen, which will follow our proton rule. So oxygen and carbon. So due to protons and octet rule is why we decided this order for this one.